Hello everyone, welcome back. So in this video, I wanted to give you a brief demonstration of NanoHub, the PN junction tool in the NanoHub to analyze PN junctions in applied bias. So we have already seen this last week. So to use this resource, you will have to go to NanoHub and then go to Tools, and then you will find PN junction lab. So if you go to P, so yeah, PN junction should be close. PN junction lab. We're using the older version. We are not using the new interactive front end. We are using the older PN junction lab. So launch the tool. And let's run the default parameters, just like what we have done in the last week. Okay. So one of the reasons I like this tool is that, I believe the best way to learn any material, any subject, is by asking questions. So you don't learn just by listening to lectures, but by actually asking questions and analyzing what's happening. So this tool is sort of a very convenient method to ask some questions and see what the answers are and whether those are consistent with our understanding. So that's what we'll try to do now. So let's take the default settings. I won't go into what the settings are. We have looked at it last video. So simulate. So we have seen the equilibrium conditions in the last week. So now let us look at IV characteristics, let's say. So it gives you the IV characteristics that we predict, exponential dependence. So here, if you extrapolate, the VT is around, I would say 0.42 or so, 0.4243, right? And then you can also look at, let's say, energy band diagram, how it changes, right? So here, this simulation default is actually running from 0 to 6 volts, or 0.6 volts rather. So this was the equilibrium at 0 applied bias. This is the equilibrium band diagram. But as you apply the voltage, forward bias voltage, you will see that there is this built-in potential or energy barrier which is reducing. And also you're seeing that the quasi-Fermi levels are separating out. This was the equilibrium Fermi level. So it will be the EFN. This will be the EFP, okay, the quasi-Fermi level for holes. So these are nicely separating out. You can compute actually, okay. And here you see some discrepancy because the length of the p-type material is only 3 microns. So in the end, there is some numerical issue. So even in this other end, you see that there is a sudden jump. This is because we are using finite number of grid points, and we are using in the end, there will be some small issue because of numerical the way it is set up. So what you could do is, I can rerun this simulation. Instead of this, I'll pick up 6 micron length. Okay, let me increase the p-type region and also increase the number of those nodes. So essentially, I'm taking this. I'm setting up the grid symmetrically in this case, and let me simulate it one more time. So by the way, so the environment is where you specify. This is the applied voltage. This is the maximum applied voltage. So right now we are setting it from 0 to 0.6. Okay, you could change that and try it out. So now if you go back and look at the, let's see, energy band diagram, we have already seen. So we could look at excess carrier density, right? So as you apply voltage, we remember that we are injecting excess minority carriers, and that's what you're seeing. Okay, so here the total is 12 microns, so 6 microns is a junction. So you see here you're injecting. So this is the holes, and this is the electrons, right? So, and we're injecting this, and you can also look at the total doping plus electron hole. So yeah, this is the regular doping densities. You'll see what happens. So if you see, yeah, as you apply voltage, you're injecting electrons from n side into the p side. That's why you see this this decay. This is a logarithmic scale, so exponential decay. So these are the minority carriers which are getting injected, and here the minority carriers are again getting injected. So I would urge you to just analyze, look at various situations. There's a lot of material here, okay? And some of which will make sense, some of which may not make sense. If it doesn't make sense, you're always welcome to ask me in the interactive sessions that we have for this course, okay? So net charge density, well, yeah, this was the kind of shape we have seen already. So this is the actual solution, right? Not with the depletion approximation. So if you looked at the charge density at equilibrium, this red curve was a depletion approximation we have seen, but the actual density was slightly different. Now we'll look at it as we apply voltage. So what do you expect as you apply voltage? The depletion region width will reduce, and that's what you will see here. As you apply voltage, you see that the depletion width is slowly reducing as you increase voltage. So just take it like an interactive tool, ask questions, and see if you can find the answers. Okay, and that's really a very good way of learning. Okay. We could also check out what happens in the reverse bias. So for that, I'll take till -1. I'll run a simulation. Okay. So, well, I have just run this before this, so I have the results already cached. Okay. So now let's look at electric field, let's say. So we saw the peak electric field was this profile at zero applied voltage. What happens as you increase the reverse bias? What happens to the peak electric field, right? So I'll put one of these in the questions in the assignment. So let's say the peak electric field was roughly about 10 power 1 into 10 power 4, right? But as you apply voltage, you will see that the electric field increases. Okay? So if I apply a voltage of let's say -1 volts, it might actually become something close to 1.5. So there is an increase in the applied electric field, right? As you apply more and more negative bias. This is because the depletion charge, if you look at net charge density, so this is a net charge at 0, and as you go to more and more negative voltages, the depletion charge is increasing, right? So that's why the electric field is larger. So electric field is simply found by integrating this charge, right? As you go from zero electric field region to the center, as you integrate, you will see that there's more and more charge, and that's why there's a stronger electric field. And because it's, of course, the same, it's related to the electrostatic potential, you will see that as you increase your applied voltage in the reverse bias, the barrier increases, potential barrier increases. Okay, all of this is consistent. So I would urge you to just explore this. Okay, let me also try out something else, which is fun. We studied what happens to reverse bias, right? Or rather, what happens to VT as you change the temperature. So this tool nicely gives you that opportunity as well. So you could run a simulation with temperature. I'll say I'll take 300 degrees, and then I'll also simulate with 350. Okay. So I'm running these two simulations. Right now is a reverse bias, so this will not actually show you the VT. We will have to rerun the simulation. But right now in the reverse bias, 300 and 350, what happens? What do you expect? What is the major impact of temperature? As you increase temperature, we have seen that the reverse saturation current increases, right? So let's explore whether that happens. Okay. So let's see. You can also plot what do you say? IV characteristics. Okay. So that essentially is telling you from 0 to -1, there is a kind of a constant current. Of course, this is not taking into account the impact ionization or Zener breakdown. Okay, that's different. We have not encountered that. We have not included that in the model. That's why it won't be captured. The breakdown won't be captured. So this is some, minus. So the saturation current is 0.18 amps per centimeter square. I don't know what the area was here assumed. That would depend on the area as well. Oh, okay, per unit area. Okay, so but this is what seems to be reasonably large actually. Let's see. Compare this with the okay at 300 degrees IV characteristics. Yeah, 0.003. I think you should not take the absolute numbers here. It's quite large, and I'm not sure if the reason is the numerical accuracy, the way we set it up. So, but at least relatively, you see that this is zero point 0.3 milliamps, and at 350 degrees it was expected to be larger, and it is actually 0.05, so 0.066 milliamps. Okay, so you see that there is a strong increase in the reverse bias current. Okay, and well, I mean, there is a whole lot of things you can check. I mean, almost lot of everything that you can think of is here. So CV characteristics. As you increase the reverse bias, the depletion width increases, because of which the capacitance reduces, right? So you see that the capacitance is reducing. This is the depletion capacitance. You could also download this data into your desktop and check 1 over C square versus uh, V. Okay, whether that gives you a straight line, you could check it out. But of course, this is not a real, one-sided junction. If you want to do that, the analysis that we have shown, right, 1 over C square versus V, if you want to verify that, you'll have to make this, let's say, 10 power 18 or so. So it becomes one-sided junction, then you get accurate results. So all this you can try by yourself. Okay. So let me just show you one last thing and I'll stop. So I'll go back to okay, this temperature, but this time I want to simulate in the forward bias. So let me do this at high temperature. It's not running. Okay, and then let me also run it at room temperature, 300 Kelvin. So you could actually compare bands slightly. There is a small change in the band gap. You see, this is at 350 degrees, and this is at 300 degrees. So you have clicked all here. So when I do that, I mean both the things are displayed. So right now it is 300 degrees. If I click all, there is a small change here in the barrier. So why this happens, you could analyze by yourself. Okay. And let's look at the current IV characteristics. So you see here, so this was at 350. 350 was threshold. Sorry, yeah, this is at 300. Sorry, 300 degrees. You have threshold voltage, close to 4.42 or something like that. And then the moment you included the higher temperature, the threshold has shifted to the left, as we have discussed in the last video, right? So the threshold voltage changes, and that's why you get larger amount of current. Okay. So, I mean, just, all I can say is this is really a gold mine. I mean, you can analyze a lot of things, there are a lot of interesting things. What is this recombination rate? If you're curious, you could explore, and then you can try to think of answers. Okay. So, yeah, I would just wish you good luck and let me know if there are any questions. All right. Have a great day. Bye.